Right now, the STEREO and SOHO space telescopes are tracking an interstellar comet designated 3I Atlas as it emerges from behind the Sun, having suddenly flared several times brighter than predicted models allowed, contradicting every theoretical framework astronomers built for extrastellar visitors, leaving scientists at the Lowell Observatory and the US Naval Research Laboratory unsettled by what they are witnessing in real time. The object completed its closest solar approach yesterday, November 5, 2025, and the data streaming back to Earth show something that should not be happening according to conventional comet physics. This is not speculation. This is measurement. The comet is accelerating in ways that gravity alone cannot explain. Observations published in the Archive repository document non-gravitational acceleration vectors that require an external force, and the leading candidates are outgassing jets composed of volatile compounds vaporizing under solar radiation. But here is what has sent ripples through the planetary science community. The spectroscopic signature shows ionized gases fluorescing in ultraviolet wavelengths, giving the coma a distinct blue tint that speaks to chemistry foreign to objects native to our solar system. Carbon dioxide, cyanide, possibly other nitrogen-bearing molecules in ratios that do not match the compositional profiles of Oort cloud comets or Kuiper belt objects. This is not a traveler from the outer reaches of our sun's influence. This is a messenger from another star, and it is behaving in ways that challenge the baseline assumptions of how icy bodies should respond to solar heating. Here's where it gets interesting. The brightness surge was not gradual. It was abrupt, a sudden luminosity increase that occurred as 3I Atlas rounded perihelion at a distance where solar flux should trigger predictable sublimation rates in water ice. But water ice sublimates in a well-understood pattern, and that pattern does not produce the kind of explosive brightening recorded by multiple observatories on November 5th. The alternative explanation involves supervolatile ices, compounds like carbon monoxide or carbon dioxide, that remain frozen at temperatures far lower than water, meaning this comet's nucleus could have been assembled in the frigid outskirts of an alien planetary system where temperatures never rose above the threshold for these substances to vaporize. When 3I Atlas plunged toward our sun, those supervolatiles encountered heat they had not experienced in billions of years, and the result was a sudden, dramatic outburst that lit up the inner solar system. Think about what that means. This object may have formed in a stellar environment where the protoplanetary disk chemistry was fundamentally different from the one that built Earth, Mars, Jupiter. It could carry in its frozen heart a record of nucleosynthesis products from a star with a different mass, different metallicity, different history of element production. Astronomers have been searching for decades for ways to sample the material composition of exoplanetary systems without traveling light years, and now a chunk of one has arrived on a hyperbolic trajectory, moving at 221,000 kilometers per hour relative to the Sun, offering a chance to analyze alien world-building blocks with instruments in Earth orbit and on terrestrial mountaintops. But scientists are cautious, and their caution is well-founded. Dr. Matthew Knight, a comet specialist whose work on interstellar object dynamics has been cited extensively since the Oumuamua encounter in 2017, emphasized in a preprint release this week that extraordinary claims require extraordinary evidence. The brightening could be a fragmentation event, where thermal stress fractured the nucleus and exposed fresh ice to sunlight, increasing the active surface area and therefore the total outgassing rate. Fragmentation is common in comets passing close to the Sun, and it does not require exotic chemistry to explain. But fragmentation events typically produce detectable debris clouds, secondary nuclei, measurable changes in rotational light curves, and so far the data from STEREO and SOHO do not conclusively show any of those signatures. The brightness increased, yes, but the coma morphology remained coherent, suggesting a single nucleus undergoing enhanced activity rather than a disintegrating body. Here's the problem. If this is enhanced outgassing from supervolatile sublimation, then the nucleus must contain a significant reservoir of these compounds, and that reservoir must be exposed to sunlight in a way that allows sustained emission. Comets are not uniform spheres of ice. They are rubble piles, agglomerations of dust, and frozen volatiles with complex internal structures shaped by collisions, accretion processes, and thermal cycling over eons. For 3I Atlas to brighten as it did, either the nucleus has an unusually high fraction of supervolatiles compared to solar system comets, or its surface properties change during perihelion passage in a way that increase the efficiency of solar energy absorption and transfer to subsurface ice. Both scenarios are plausible, but neither is confirmed. And the uncertainty is precisely what makes this observation so scientifically tantalizing and so frustrating in equal measure. Now about the data. The comet's trajectory is perfectly hyperbolic with an orbital eccentricity greater than 1, meaning it is not bound to the Sun and will never return after this single passage through the inner solar system. Its velocity at infinity, the speed it will asymptotically approach as it escapes the Sun's gravitational influence, is approximately 37 kilometers per second. To put that in perspective, that is fast enough to cross the distance from New York to Los Angeles in less than 2 minutes. It is a speed that can only be achieved by an object that either formed in orbit around another star and was ejected by gravitational interactions with a massive planet, or by an object that was accelerated by a close encounter with a stellar remnant, possibly even a black hole, though the latter scenario is far less likely given the rarity of such encounters in the galactic disk. The velocity itself encodes information about the comet's origin. Objects ejected from planetary systems during the planet formation process typically leave with speeds in the range of 10 to 50 kilometers per second relative to their parent star, depending on the mass of the planet doing the ejecting and the geometry of the encounter. A velocity of 37 kilometers per second is well within that range, suggesting that 3I Atlas was flung out of its home system by a gas giant, perhaps a Jupiter-class planet or larger, during the chaotic early epochs when planetary architectures were still stabilizing and massive bodies were migrating inward or outward due to interactions with the protoplanetary disk. If that scenario is correct, then this comet is a fossil from the era of planet formation in another stellar system, a time capsule that has been traveling through interstellar space for potentially billions of years, exposed to cosmic rays, interstellar dust impacts, and the faint light of distant stars before finally crossing paths with our Sun. Stop and consider that. Billions of years. The universe is 13.8 billion years old. The Sun and Earth formed 4.6 billion years ago. If 3I Atlas originated in a system that is older than ours, it could carry chemical signatures from an epoch when the Milky Way's metallicity was lower, when the abundance of heavy elements like carbon, oxygen, nitrogen, and sulfur was different from what we see in the solar system. Spectroscopic analysis of the coma could reveal isotopic ratios that diverge from solar system norms, providing direct evidence of nucleosynthesis in a different stellar environment. Deuterium to hydrogen ratios, carbon-12 to carbon-13 ratios, nitrogen-14 to nitrogen-15 ratios, all of these are potentially measurable in cometary ices, and all of them carry information about the temperature and density conditions in the protoplanetary disk where the comet formed, as well as the nuclear burning history of the star that dominated that environment. But there is a catch. Cometary coma spectroscopy is not trivial. The signals are faint, the molecules are often dissociated by solar ultraviolet radiation within seconds to minutes of leaving the nucleus, and the resulting fragments produce overlapping emission lines that require careful modeling to disentangle. Ground-based observatories equipped with high-resolution spectrographs are tracking 3I Atlas as it moves away from the Sun, but the comet is currently located in a region of sky that places it in the solar glare, making observations difficult until it reaches a greater angular separation. According to orbital predictions, 3I Atlas will become visible in amateur telescopes starting November 11th in the constellation Virgo, low in the eastern sky before dawn. That is less than a week away. And professional observatories are already scheduling observing runs to capture spectra during the most favorable viewing window. The European Space Agency's JUICE spacecraft, currently en route to Jupiter, has redirected some of its remote sensing instruments to scan the comet's tail. JUICE was not designed for comet science, but its ultraviolet spectrograph and visible imagers are capable of detecting emission lines from ionized species in the coma, and the mission operations team saw an opportunity to contribute valuable data to the investigation. The spacecraft is not in an ideal position for prolonged observations, but even a few hours of coverage could reveal the presence of molecules that are difficult to detect from Earth due to atmospheric absorption: water, carbon monoxide, carbon dioxide, methane, ammonia, formaldehyde, methanol. The list of potential cometary volatiles is long, and each species tells a different part of the story about where and how the comet formed. Here's where things get strange. The non-gravitational acceleration is not uniform. Preliminary analysis of the trajectory deviation suggests that the outgassing is asymmetric, concentrated in one hemisphere of the nucleus, or possibly emanating from discrete active regions that rotate in and out of sunlight as the nucleus spins. Comets are known to have jets, localized sources of gas and dust emission that can create torques on the nucleus and alter its rotation state over time. What makes the 3I Atlas jets noteworthy is the magnitude of the acceleration. The force required to produce the observed trajectory change is substantial, implying either a very high outgassing rate or a relatively low nucleus mass, or both. If the nucleus is on the smaller end of the size estimates, around 320 meters in diameter, then the mass would be correspondingly low, and even modest outgassing could produce measurable acceleration. But if the nucleus is several kilometers across, as the upper end of the size range suggests, then the outgassing rate would have to be enormous to generate the observed effect. And that raises questions about how much volatile material the nucleus can contain and how long the activity can be sustained. Dr. Alan Fitzsimmons, an astronomer at Queen's University Belfast, who has studied both Oumuamua and Comet 2I Borisov, the first two confirmed interstellar objects, noted in a recent interview that size estimates for these visitors are notoriously uncertain. Without resolved imaging, astronomers rely on brightness measurements and assumptions about surface reflectivity, or albedo, to infer size. Dark surfaces reflect little sunlight, meaning a faint object could be either small and bright or large and dark. Cometary nuclei are typically very dark, with albedos around 4%, similar to charcoal, because the surface becomes coated with refractory organic residues as volatile ices sublimate over repeated solar passages. But 3I Atlas has never passed our sun before, and if it formed in a colder environment with different chemistry, its surface properties might not match those of solar system comets, meaning the standard albedo assumptions could be wrong, and the true size could lie anywhere within the estimated range of 320 meters to 5.6 kilometers. Read between the lines of the observational reports, and a pattern emerges. Scientists are being very careful with their language. They describe the brightening as unexpected, but not impossible. They acknowledge the non-gravitational acceleration, but frame it as consistent with known physical processes. They emphasize the need for more data, better spectra, longer observing campaigns. This is the language of caution, the professional reluctance to overinterpret preliminary results, and it is entirely appropriate. But beneath that caution is a current of genuine excitement, because regardless of the final explanation for the brightness surge, 3I Atlas is the third confirmed interstellar object to visit the inner solar system, and each one has been different. Oumuamua showed no detectable cometary activity and had an elongated shape that sparked all manner of speculation, including the controversial hypothesis that it might be an artificial object, a suggestion that was scientifically explored and ultimately deemed unnecessary given plausible natural explanations. Comet 2I Borisov looked and behaved like a textbook comet, with a well-developed coma and tail and a composition that closely matched solar system comets. And now 3I Atlas arrives with a brightness outburst and unusual spectroscopic features, adding a third data point to a sample that is slowly revealing the diversity of objects wandering between the stars. Think about what that means for the architecture of planetary systems in the galaxy. Every star with planets likely produces a population of small bodies, asteroids, and comets that form as byproducts of the planet-building process. Some fraction of those small bodies are ejected into interstellar space, either by gravitational scattering during the early chaotic phase, or by perturbations from passing stars later in the system's history. The rate of ejection depends on the number and masses of planets, the density of the protoplanetary disk, the frequency of close stellar encounters, and other factors that vary from system to system. Given that there are hundreds of billions of stars in the Milky Way, the total population of interstellar small bodies must be staggering. An invisible swarm of asteroids and comets drifting through the galactic disk, occasionally passing through other stellar systems and offering a brief opportunity for detection and study. Until 2017, no interstellar object had ever been confirmed, despite decades of searching. The discovery of Oumuamua changed that, proving that such objects exist and are detectable with modern survey telescopes. The discovery of 2I Borisov in 2019 and now 3I Atlas in 2025 suggests that detections are becoming more frequent, likely because survey capabilities have improved and because astronomers know what to look for. But the detection rate is still very low, a few objects per decade, and that low rate places constraints on the space density of interstellar visitors in the solar system's neighborhood. Current estimates suggest that at any given time, there might be one interstellar object within the orbit of Neptune, an object that arrived from elsewhere and is passing through unseen and undetected unless it happens to pass close enough to the Sun to become active and bright. The implications are profound. If the Milky Way is full of interstellar comets and asteroids, then the exchange of material between stellar systems is not a rare event, but a common, ongoing process that has been happening for billions of years. Comets carry not just ice and dust, but also organic molecules, the carbon-based compounds that are the building blocks of life as we know it. Laboratory studies of meteorites and comet samples have shown that these materials contain amino acids, nucleobases, sugars, and other prebiotic molecules, raising the possibility that the ingredients for life could be delivered to planets by cometary impacts. If comets are also traveling between stars, then the distribution of organic molecules could be galactic in scale, not confined to individual stellar systems. This is the panspermia hypothesis in a new form, not life itself spreading between worlds, but the chemistry of life, the molecular toolkit that makes biology possible, being redistributed across interstellar distances by natural processes. Dr. Karen Meach, an astronomer at the University of Hawaii who led much of the early observational work on both Oumuamua and 2I Borisov, has argued that interstellar objects are a new frontier in comparative planetology, a way to study planet formation in other stellar systems without needing interstellar spacecraft. Every detection provides a new piece of the puzzle, a new constraint on the diversity of compositions, structures, and dynamical histories that small bodies can have. If 3I Atlas truly has a different chemistry from solar system comets, that difference tells us something about the conditions in its home system, the temperature gradient in the protoplanetary disk, the inventory of volatile species available during planet formation, the timing and efficiency of gas giant migration, all the factors that shape the final architecture of a planetary system. But identifying that home system is nearly impossible with current data. The comet has been traveling through interstellar space for so long that its trajectory no longer points back to any specific star. Galactic dynamics, the gravitational influence of the Milky Way's disk and spiral arms, have altered its path over millions or billions of years, erasing the information about where it came from. Tracing the orbit backward through the galaxy requires knowing the comet's position and velocity with extreme precision, and even then, the uncertainties multiply rapidly as the integration runs further into the past. Some researchers have attempted to calculate probable origin regions for Oumuamua and 2I Borisov, and the results typically point to broad areas of the sky containing hundreds or thousands of stars, making it impossible to identify a unique source. The same will almost certainly be true for 3I Atlas. Its origin will remain a mystery, knowable only in a statistical sense, a member of the population of ejected objects produced by some unknown planetary system somewhere in the galactic neighborhood. That uncertainty is frustrating, but it does not diminish the scientific value of studying the object while it is accessible. The observational window is limited. 3I Atlas is moving away from the Sun at 61 kilometers per second, fast enough that within a few months it will fade beyond the reach of all but the largest telescopes. In December, it will reach its closest approach to Earth at a distance of 270 million kilometers, roughly 1.8 astronomical units, still far beyond the orbit of Mars, but close enough that the comet will subtend a measurable angular size in high-resolution images. Ground-based observers are planning imaging campaigns to search for structure in the coma, asymmetries in the dust distribution, possible fragmentation signatures, anything that could provide insight into the nucleus's physical properties. The SETI Institute, an organization that searches for signs of extraterrestrial intelligence, has announced that it will be using radio telescopes to scan 3I Atlas for any artificial signals. This is not because anyone seriously expects the comet to be transmitting, but because the scientific method requires checking even low-probability hypotheses when the opportunity arises. The same logic was applied to Oumuamua, which was observed with the Green Bank telescope to search for radio emissions, and none were detected. The absence of a signal does not prove the absence of technology, but it does place limits on the brightness and frequency of any hypothetical transmitter, and those limits are scientifically useful. If 3I Atlas turns out to carry any unusual spectroscopic features in the radio or microwave bands, those features will be documented and analyzed, and natural explanations will be explored first, because nature has produced an astonishing variety of phenomena that can mimic artificial signals, from pulsar pulses to master emission from molecular clouds. Here's where the narrative splits into competing interpretations, each supported by different subsets of the data, each with its own adherents among the scientific community. The first interpretation, and the most conservative, is that 3I Atlas is simply a comet, no different in principle from the billions of comets in the Oort cloud, except that it formed around another star. The brightness surge is outgassing. The blue tint is ionized gas. The non-gravitational acceleration is rocket-like emission from jets, all phenomena that have been observed in countless solar system comets and are well understood within the framework of cometary physics. The unusual aspects, the timing and magnitude of the brightening, the specific spectral features, are variations within the natural range, perhaps the result of compositional differences, but not indicative of anything fundamentally exotic. This interpretation requires no new physics, no unknown processes, and it is consistent with the principle of parsimony, the idea that the simplest explanation that fits the data is usually correct. The second interpretation is more speculative but still scientifically defensible. It holds that 3I Atlas is representative of a different class of comets, objects that formed in colder, more volatile, rich environments than the comets native to our solar system. In this view, the Oort cloud and Kuiper belt formed from material that condensed in the outer solar nebula, where temperatures allowed water ice to be the dominant volatile, but where compounds like carbon monoxide and nitrogen remained in the gas phase and were not efficiently incorporated into solid bodies. But in stellar systems with different disk properties, lower temperatures, or higher abundances of carbon and nitrogen, supervolatile rich comets could be common, and 3I Atlas might be an example of such an object. If this is correct, then spectroscopic follow-up should reveal high abundances of carbon monoxide, carbon dioxide, and nitrogen-bearing species relative to water, a chemical signature that would distinguish it from typical solar system comets and provide strong evidence for a different formation environment. The third interpretation is the most provocative and the least supported by current evidence, but it cannot be dismissed outright without further data. This interpretation suggests that the brightness surge and non-gravitational acceleration are not entirely explained by passive outgassing but involve some active process, possibly an internal heat source or a structural change in the nucleus that increased the surface area or altered the thermal conductivity. Comets are known to undergo sudden outbursts, sometimes triggered by the collapse of subsurface voids or the exposure of fresh ice by impacts from meteoroids. These outbursts can be dramatic, increasing the brightness by factors of 10 or more in a matter of hours, and they do not require exotic mechanisms. But if the 3I Atlas outburst was triggered by an internal heat source, perhaps residual radioactive decay from short-lived isotopes that have long since decayed in solar system objects but might still be present in a comet from an older stellar population, that would be a significant finding, because it would imply that the comet's interior has remained thermally active over timescales far longer than expected. None of these interpretations is confirmed. All of them are hypotheses awaiting better data. And that is the state of the science right now, a moment of uncertainty and anticipation as observations continue and analyses proceed. The data released so far are preliminary, based on rapid turnaround processing of images and spectra obtained during the perihelion passage. More refined measurements will take weeks or months to produce, as astronomers calibrate their instruments, subtract background light, correct for atmospheric and instrumental effects, and compare their results with theoretical models. The scientific process is deliberate and careful, designed to minimize errors and false positives, and it does not produce instant answers. But the clock is ticking. Every day that passes, 3I Atlas moves farther from the Sun and becomes fainter. The opportunity to study this object in detail will not last long, and there is no guarantee that another interstellar comet will appear anytime soon. The discovery rate of roughly one object every 2 to 3 years is an average, not a constant, and it is entirely possible that the next detection could be years away. So the pressure is on the observational community to collect as much data as possible, while 3I Atlas is still bright enough to study, to deploy every available instrument and technique, to coordinate observations across multiple wavelengths and multiple platforms, to ensure that when the comet fades into the distance, Mitsubishi Baines Hepaconic, the scientific community has extracted the maximum possible information from this fleeting encounter. The broader implications extend beyond the immediate science of this particular comet. The detection and characterization of interstellar objects is a young field, not even a decade old, and it is still developing the methodologies and infrastructure needed to study these visitors effectively. Survey telescopes like the Vera C. Rubin Observatory, currently under construction in Chile and expected to begin operations in the near future, will revolutionize the detection rate, potentially finding dozens or even hundreds of interstellar objects per year once the system is fully operational. That increase in detections will enable statistical studies of the population, measurements of size distributions, compositional trends, dynamical properties, all the kinds of analysis that are impossible with a sample size of 3, but become feasible with sample sizes in the dozens or hundreds. But detection is only the first step. Characterization requires follow-up observations, spectroscopy, photometry, polarimetry, techniques that demand large amounts of telescope time on facilities that are already heavily oversubscribed. The community will need to develop rapid response protocols, automated systems that can recognize an interstellar visitor from its orbital elements and immediately trigger follow-up campaigns before the object fades. Some of that infrastructure is already being put in place, but it is a work in progress. And the current response to 3I Atlas is a test of how well those systems function under real-world conditions. There is also the tantalizing possibility of a dedicated mission to an interstellar object, a spacecraft that could rendezvous with one of these visitors and conduct close-up studies that are impossible from Earth. Such a mission would be technologically challenging because interstellar objects are moving very fast and are only in the inner solar system for a brief time, meaning a spacecraft would need to be pre-positioned or capable of extremely high delta-V maneuvers to intercept. The European Space Agency studied a mission concept called Comet Interceptor, designed to be parked at the Sun-Earth L2 point and launched toward a newly discovered long-period comet or interstellar object when a suitable target appears. The mission is currently in development, with a planned launch in the late 2020s, and it represents the first serious attempt to build the capability to study these objects up close. If Comet Interceptor were already operational, 3I Atlas would be an ideal target. But the spacecraft is still years away from launch, and by the time it is ready, this comet will be long gone. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury, who specializes in outer solar system and interstellar objects, has argued that the scientific community should treat every interstellar visitor as a unique opportunity that may not come again. The diversity seen so far, Oumuamua with no activity, 2I Borisov with typical cometary behavior, and now 3I Atlas with an unusual brightness surge, suggests that the population is heterogeneous, and every detection adds a piece to the puzzle. But with only 3 examples, the puzzle is still mostly blank, and major questions remain unanswered. What fraction of interstellar objects are active comets versus inert asteroids? How do their compositions compare to solar system objects? Are there objects in the population that have no analog in the solar system, bodies that formed under conditions we have not yet considered? These are questions that will require many more detections to answer, but each new object brings the field closer to a comprehensive understanding. Stop and consider that the very existence of interstellar objects was uncertain until a few years ago. Theoretical predictions suggested they should exist, that planetary systems should eject material into interstellar space, and that some of that material should occasionally wander into our solar system. But predictions are not the same as observations, and the history of astronomy is full of predicted phenomena that turned out not to exist or that behaved differently than expected. The detection of Oumuamua was a watershed moment because it confirmed that the predictions were correct, that these objects are real and detectable, and that opened the door to an entirely new field of study. Now, less than a decade later, the field is beginning to mature, accumulating data, refining models, developing the tools and techniques needed to make the most of future discoveries. The timing of 3I Atlas's arrival is fortuitous in another way. It comes at a moment when multiple new instruments are coming online or are under development. Instruments designed to study faint, fast-moving objects with unprecedented sensitivity and precision. The James Webb Space Telescope, which began science operations in 2022, has infrared capabilities that could potentially detect thermal emission from a cometary nucleus or measure the temperature and composition of the coma with far greater accuracy than ground-based telescopes. JWST's observing schedule is set years in advance, and obtaining directors' discretionary time for a target of opportunity is difficult. But if the case can be made that 3I Atlas presents a unique scientific opportunity, there is a possibility that observations could be scheduled. Similarly, the Nancy Grace Roman Space Telescope, planned for launch in the next few years, will have survey capabilities that could detect interstellar objects farther from the Sun, extending the observational window and allowing for longer-term monitoring. On the ground, the next generation of extremely large telescopes, the Extremely Large Telescope in Chile, the 30-meter telescope in Hawaii or the Canary Islands, and the Giant Magellan Telescope in Chile, will have the light-gathering power and spatial resolution to study cometary nuclei in unprecedented detail, resolving surface features, detecting local variations in composition, and tracking changes in activity over time. These facilities are still under construction, years away from first light. But when they come online, they will transform cometary science in the same way that Hubble and JWST transformed exoplanet science, by providing data of a quality that was previously unattainable. But those future capabilities do not help with 3I Atlas today. The observations are being made with the instruments currently available: ground-based telescopes of 1 to 10 meters in diameter, space telescopes like SOHO and STEREO, that were designed for solar physics but happen to have fields of view that include the comet, and opportunistic observations from missions like JUICE that were not designed for this kind of target, but can contribute valuable data nonetheless. It is a patchwork of capabilities, not an optimized observing campaign, but it is what the community has to work with. And the results, preliminary as they are already reshaping our understanding of what interstellar comets can be. Now about the data in more detail. The blue tint observed in the coma is caused by ionized carbon monoxide, a molecule that fluoresces strongly in ultraviolet light and emits in the blue part of the spectrum. Carbon monoxide ice sublimes at temperatures around 25 Kelvin, far lower than the 150 Kelvin sublimation temperature of water ice, meaning it can remain frozen at much greater distances from the Sun. If the 3I Atlas nucleus contains significant amounts of carbon monoxide ice, that ice would begin to sublimate as the comet approached the Sun, releasing gas that is then ionized by solar ultraviolet radiation, producing the observed blue emission. The intensity of the emission is proportional to the production rate of carbon monoxide, and the production rate depends on the surface area of exposed ice, the temperature of the nucleus, and the abundance of carbon monoxide in the ice matrix. High emission intensity suggests either a high abundance or a large active surface area, or both. The presence of cyanide, mentioned in the preliminary reports, is also significant. Hydrogen cyanide is a common cometary volatile, detected in virtually every comet that has been studied spectroscopically. It is a tracer of nitrogen chemistry in the coma, and its abundance relative to water provides information about the nitrogen inventory in the nucleus. In solar system comets, the ratio of hydrogen cyanide to water is typically around 0.1 to 0.2%, meaning hydrogen cyanide is a minor constituent. If 3I Atlas shows a higher ratio, that could indicate a nitrogen-rich formation environment, or it could reflect differences in how nitrogen was incorporated into ices during the comet's formation. Cyanide compounds are also of interest from an astrobiological perspective because they are precursors to amino acids under certain chemical conditions, and the delivery of cyanide-rich cometary material to the early Earth might have contributed to the prebiotic chemistry that eventually led to life. The shape of the dust tail provides additional clues about the nucleus's activity. Dust grains ejected from the nucleus are pushed away from the Sun by radiation pressure, the force exerted by sunlight on small particles. The trajectory of each grain depends on its size and composition, with smaller, lighter grains being pushed more strongly than larger, heavier ones. The result is a fan-shaped tail that spreads out in the anti-solar direction, with the size distribution of grains encoded in the brightness profile of the tail. Observations of 3I Atlas show a tail that is described as teardrop-shaped suggesting that the size distribution is relatively narrow, dominated by grains in a specific size range. This is consistent with active outgassing from discrete jets rather than uniform sublimation from the entire surface, because jets tend to entrain dust in a more selective way, carrying grains of a certain size range more efficiently than others. The nucleus diameter estimate, ranging from 320 meters to 5.6 kilometers, is based on the observed brightness and assumptions about the surface albedo. If the albedo is 4% similar to typical comets, then the faint brightness implies a small nucleus, around 320 meters. But if the albedo is higher, say 10 or 15%, then the same brightness could correspond to a larger nucleus, several kilometers across. The difference matters because the mass scales with the cube of the diameter, so a 5-kilometer nucleus has roughly 4,000 times the mass of a 320-meter nucleus, and that has profound implications for how much volatile material it can contain and how long it can sustain activity. Determining the true size will require either resolved imaging, which is not feasible at the comet's current distance, or careful modeling of the rotational light curve, which requires multi-night photometric observations spread over several weeks. The trajectory analysis is particularly intriguing because it constrains the comet's recent history. The hyperbolic orbit, with eccentricity greater than 1, proves that the comet is not bound to the Sun, but the specific value of the eccentricity and the inclination of the orbit relative to the ecliptic plane provide information about the comet's velocity and direction when it entered the solar system. Preliminary calculations suggest that the comet came from the direction of the constellation Pisces, roughly the plane of the ecliptic, but the exact trajectory will require more data to refine. Backward integration of the orbit, accounting for planetary perturbations, could in principle determine where the comet was millions of years ago. But the uncertainties grow rapidly, and the results become speculative beyond a few million years. The close approach distance of 270 million kilometers in December is far beyond any practical mission intercept distance, but it is close enough that Earth-based radar facilities might be able to detect the nucleus and measure its size and rotation directly. Radar observations of comets are challenging because cometary nuclei are small and relatively radio dark, but the technique has been successfully applied to a handful of comets in the past, and if 3I Atlas is on the larger end of the size range, there is a chance that radar echoes could be detected with the Goldstone or Arecibo facilities. Arecibo was damaged and subsequently decommissioned in 2020, but Goldstone remains operational, and radar observations are planned for December if the comet's brightness holds up. Here's where it gets interesting from a citizen science perspective. The announcement that 3I Atlas will be visible in amateur telescopes starting November 11th has generated significant interest among amateur astronomers around the world. Citizen science projects like the AAVSO Comet Section and the Comet Observation Database have mobilized their networks to collect photometric and positional data on the comet. And the sheer number of observers involved means that the light curve will be sampled far more densely than would be possible with professional facilities alone. Amateur contributions to comet science have a long history, dating back to the earliest telescopic observations, and the tradition continues today with modern digital cameras and software tools that allow amateurs to produce data of near-professional quality. The potential for exotic substances in the comet's composition raises the question of what exactly is meant by exotic. In the context of cometary chemistry, exotic typically refers to molecules that are rare or absent in solar system comets, but might be common in other environments. Candidates include interstellar molecules like methanol, formaldehyde, and ethylene glycol, which are detected in molecular clouds and protoplanetary disks, but are not abundant in solar system comets, possibly because they were destroyed or altered during the comet's formation. If 3I Atlas shows high abundances of these species, it would suggest that the comet formed in an environment where these molecules were stable and efficiently incorporated into ices, providing a direct link to the chemistry of its birth environment. Read between the lines of the SETI Institute's announcement, and there is an implicit acknowledgement that the search for signals is as much about ruling out possibilities as it is about finding something. The absence of a detectable artificial signal from Oumuamua was scientifically valuable because it placed limits on the hypothesis that the object might be a probe or artifact, a hypothesis that was always low probability but gained traction in the media due to the object's unusual shape and lack of cometary activity. The search for signals from 3I Atlas serves the same purpose, providing a data point that future studies can reference if questions arise about the object's nature. It is an example of scientific due diligence, checking even unlikely possibilities when the cost of checking is low and the potential payoff, however small, is high. The mention of a black hole as a possible mechanism for the comet's ejection from its home system is intriguing but requires context. Stellar mass black holes are the remnants of massive stars that have undergone core collapse, and they are relatively common in the galaxy, with an estimated population of tens to hundreds of millions. Most of them are isolated, not in binary systems, and they are effectively invisible except when they are accreting matter and emitting X-rays. A close encounter between a planetary system and a passing black hole could gravitationally disrupt the system, ejecting planets and small bodies at high velocities, but such encounters are rare, far rarer than encounters with ordinary stars, because black holes are far less numerous than stars, and because their small size means the cross-section for a close encounter is small. The velocity imparted by a black hole encounter could be higher than that from a planetary scattering event, but it is not necessary to invoke a black hole to explain 3I Atlas's velocity, which is well within the range expected from planetary ejection. The phrase zigzagging through the galactic disk is a poetic but somewhat misleading description of the comet's motion. In reality, the comet is moving on a smooth trajectory through space, its path determined by the gravitational fields of the Sun, the planets, and the galaxy as a whole. The path may appear to zigzag from the perspective of an observer on Earth because of the relative motion between Earth and the comet, but in an inertial reference frame, the comet's motion is smooth and predictable, governed by well-understood physics. The trajectory is hyperbolic relative to the Sun, meaning the Sun's gravity deflects the comet's path but does not capture it. And after the deflection, the comet continues on into interstellar space, its velocity altered slightly by the encounter, but still sufficient to escape the solar system.